To others, good afternoon. Welcome to this tutorial on developing a testing and continuous integration strategy for your team. Once again, I'd like to encourage everybody to visit the URL at the bottom of the page, bssw-tutorial.github.io, and find the page for today's tutorial, where you can find a link to the slides as well as a bunch of other information from the tutorial. And we'll echo that in the chat again. Pat or Jim, if you can get a chance to just retype that for the recent people who joined recently, that would be great. In our presentations, you'll see always the second slide, this license, citation, and acknowledgement slide. So we're making this available under a Creative Commons license. There is a citation that we request you use if you want to reference the tutorial in any formal context. There's a lot of people who have contributed to this tutorial over the years, and of course we want to thank especially the ECP project for financial support for this work. And in the future slides, we're just going to skip through this, so I should turn on my video too. All right, so we'll move on. So I'm David Bernhold from Oak Ridge National Laboratory. With me presenting today will be Patricia Grubel from Los Alamos and James Willenbring from Sandia. And we're members of the Ideas Productivity Project, which has a focus as part of the ECP and has a focus on increasing software productivity, quality, and sustainability for computational science and engineering software. So just a second about the ECP, Ideas ECP project. We work with the ECP community and the broader HPC, computational science and engineering community in a variety of ways to try to improve developer productivity and software sustainability as key elements of scientific productivity. And the slide kind of illustrates some of the ways, different ways that we can engage. You can find out more about our project if you want to join us on Wednesday in the lower right. You can see we have a BOF, Wednesday 11:30 Eastern, or we have a project report that you can access. These links are available on the website and in the PDFs of the slides. Another aspect of our work is the Better Scientific Software online community, bssw.io. You may have heard of this. This is a website which is meant to serve as a central hub for information about good software practices and related information. It's meant to be a community resource, not only people reading, but also sharing your own resources that you found useful. So we encourage you both to read and contribute based on your experiences. And then if you're interested after hearing this or from other things in following more about our project activities, that we have a mailing list where we announce things like our webinar series and remote work panel series, as well as major events that we help organize at scientific meetings. This is just typically a couple of messages a month. And then we have the BSSW Digest, which comes out monthly, which highlights new postings on the site, bssw.io site. The objectives for our tutorials are try to talk about best practices in software engineering, explicitly tailored for computational science and engineering. We mean these to be generally applicable, but we try not to be dogmatic about it. We're trying to present useful information and examples and not prescribe anything necessarily as must use. Something else you'll hear several times throughout this tutorial is that we recommend undertaking a series of small incremental improvements to build up your software practices and improve your processes. And that we think can help you get into these to better software practices in a stepwise fashion rather than having to take some huge step all at once. And of course, you should customize these practices as needed for your project. One of the main points that we want to present in our tutorials is that your code will live longer than you expect, so you should start preparing for it now. We do want to interact with you. We find these tutorials most interesting for us and for the participants. If you ask questions and share experiences, I know this is a little bit harder to do or harder to sort of engage in the online context, but please try to do that. We learn a lot too from interacting with you. We would ask that you use the chat for questions at any time, and we'll answer in either the chat or verbally as we can. And then as time permits, we'll also take questions at the end of presentations. I think this will be a relatively relaxed presentation, so I'm hoping that we'll have some time for discussion, but don't let that stop you from posing your questions as you go along. After the tutorial, you can reach us at BSSW tutorial mailing list, or you can also visit us during this week at this ideas desk. We're just going to have an informal place in the side meeting room in Gathertown, where there'll be some ideas participants ready to talk about software productivity and sustainability with anybody who wants to drop by. And then also I wanted to highlight these other events during the annual meeting, which are not only ours, but are particularly related to testing and continuous integration and software process improvement. So with that, I'm going to hand it over to Pat, who will start the overview module for our tutorial.
Okay, I'm going to start up my video, I think. Okay. Should work, and I will start sharing. Just go ahead and share the desktop because I have to switch to different. So can you see my slides?
Yep, you're good.
Okay, so first of all, I'm going to give you motivation and then an overview of our tutorial today. And what I want you to think about is that science through computing is at best as credible as the software that produces it. Now, here are a couple of examples that I wanted to go through that show some high consequence failures due to software, scientific software in particular. In the Therac 25 was a computer-controlled radiation therapy system, and due to poor software design, development, and testing practices, there were flaws that caused injuries and even fatalities. And then you might know about the Mars Climate Orbiter that was lost due to incorrect trajectory adjustments. It was caused by one component that didn't follow specifications, and on top of that, there were inadequate testings at the interface level. And although concerns were raised earlier, they weren't ever documented in good bug reports, so they weren't fixed. And these are just two of many examples. What I want you to do is think about what your scientific application, what kind of consequences could happen from it, and what are the implications of what you're actually doing. Or you may be creating policy or policies created because of your software, or you may even have physical aspects like these two cases. So there are many challenges when developing scientific application. The models are under research, so they can be fluid. It can be changing as the research comes up with knowledge from them. Requirements change throughout the life cycle because our knowledge grows. And then all scientific software uses floating point representation, so verification can become very complicated. And the real world is messy, and the software ends up being messy also when we're trying to model the real world. And of course, all of you know, because you're at this ECP conference, that our architecture is continually changing, and the software needs to adapt to that and use it in different ways than it was maybe designed initially. And so that also complicates the technical aspects. And then you have sociological aspects that may cause teams to kind of cheat or because they're more in tune to doing things like getting their publications out, so they may skip on tests. So these are things we have to be aware of. And then we have limited resources. We don't always have all the allocations we'd like to have, so we have to consider that. And our teams are made up of different specialties, and sometimes the priorities are a little different. We have to work together to make sure that we fulfill the challenges that come with our application. So here are some of the best practices. This tutorial, again, is going to primarily focus on scientific software, which is a little different than the more generic software engineering best practices. And we're going to look at the big things are instituting rigorous verification and validation, and defining and enforcing coding and testing practices and standards. So there are many categories of testing. During the development process, you'll hear about different types of testing, including unit, functional, integration, system regression, all sorts of tests. Sometimes you'll hear the term smoke test. What is that? Well, many times those are simple tests that are used to verify that your build and install process has succeeded. And those are usually a subset of the development tests, and they take just a few minutes, but they don't give you a complete test, and that's why they're just called smoke tests. And then we have continuous integration tests. They're usually run very quickly and are usually automated. There'll be a lot of talk about that later in this talk, and then there's, as David pointed out, there's other talks this week that include that. So what are the challenges when it comes to testing these complex software systems that we use in scientific applications? A lot of times there's a large network of interdependencies, which can include scientific libraries, can include modules from other applications, and that makes it very hard to test them, your software. And then also, some cases cannot be actually tested prior to implementing the software. So what you need to do is come up with the ways to do this. Sometimes we're working with legacy code, and a lot of times legacy code is either untested or it doesn't have very much coverage and it's tested. So then we have to progressively improve the code coverage and understand the software. The key developers are often not available to test the legacy software. And then we all think we want to have automated tests, but you have to start with some tests before you can actually automate them. So if you don't have automated tests, start thinking about what things can be automated. And then also you need to consider your resources, and this is for both maybe continuous integration and for your large tests that are more regressive testing. And so you have to consider what you have available to you and what the tests are used for. Testing is a large subject, and we're not going to be able to cover it all today, but we'll cover some of it and get you started. Again, Dave mentioned this. Sometimes what you want to do a continual but incremental process improvement, and we have the PSIP project that we call, which stands for Productivity, Sustainability, and Improvement Planning. And a lot of times you can find something in your pain process that you can put a little bit of time into, and it improves quite a bit in the future. Do this in an incremental manner. Don't try to do everything at once. Look at processes as well as tasks. And so that is the end of the motivation, and I'm going to move on to software testing. And if there's any questions as I go, if you need me to address them, one of the team members can let me know. Let me switch to my other. And make sure you're seeing this. Okay, we're going to talk about software testing. You'll see there are two small talks, and David will continue. The first one is more about strategy, and the second one will go into some examples and experience from our team and get into a little bit more detail. First of all, I wanted to talk about verification and validation. So code verification uses the tests that you might build, but it's more than the collection of these tests. It's a holistic process that you would go through to ensure that your implementation actually behaves as you expected it to, that you designed it to. And then you need to make sure it's consistent with the mathematical and physical models that you are attempting to implement. And finally, you want to make sure that the science that you're trying to do can be done with this code. So there are two different definitions of, a lot of times these are interchange, verification and validation. And so what we're talking about is that verification, you confirm what you meant to do, and validation is a little bit harder. It is more of an outward-looking process, and it ensures that the science phenomenon that you're trying to understand is actually correctly captured in the code. And one thing you can think about when you're doing this is that your model, if your code has been implemented correctly, it can either disprove or approve the science that you're trying to verify. Now, during this verification, you have different types of stages. It's different for verifying during initial code development. As the code matures in later stages, you will be thinking about verification in a different manner. So as you're developing your code, you want to look at the stability and the accuracy. Stability as changes are putting in there, make sure that the components are still behaving as they should. And then you want to make sure that you are actually matching the algorithm to the mathematical models that you are implementing. And as you are going, you have to develop tests that show that the algorithms are operating in a manner where their interoperability is not changing this accuracy and the stability of the components. In later stages, you may have a code or an application that is very mature, but now you have decided to add new capabilities or even just modify some of the existing ones. So you need to have some testing that you can continue with, or you may have to modify them or even make new tests. And then there's always ongoing maintenance. As you're fixing any bug issues that come up from either your users or from your tests, you need to be able to make sure that your testing is still valid and working for your system. And then there's a whole other idea when you are preparing for production. This is when you want to put the codes out on the production system. You need a comprehensive set of tests that make sure that the users will be able to use this code the way that is intended. And you also may have to look at some unique things that the users are using with your application that you hadn't thought of. So then there are components of verification. There are different granularity levels. There are individual components that you will have tests for. And then you have to consider the interoperability between these components, even on those component tests, and maintain convergence when it's applicable, and accuracy, and of course the stability of your components. So what you can do is build diagnostics, ensure that these quantities are valid in the individual components. And in these testing practices, you need to look at your errors. What are the tolerances in your system on these error bars? How do they change when you're doing things like parallel processing and using multi-threading, and differentiate between drift and round off that may be caused by this, and make sure that everything is still stable and accurate and into the tolerances that your system can accept. So why not use the most stringent test? I want to test everything. Well, the effort in devising and running and also maintaining your test suite, it can be substantial, and it makes a tax on your team. So your team is having to balance out meeting code use objectives and also maintaining, developing these test suites. And so you have to balance that out. If the tax is too high, then you can't meet those code use objectives. And if it's too low, then you don't have the necessary oversight to prevent defects sneaking into your code, which can cause big problems. So you have to evaluate your project needs. What is the expected use of the code? Maybe you don't need to test every part of the code because some parts aren't going to be used. You need to look at the experience, the size, and the expertise in your team and what can be put on these parts of the code. Also, it's different for different life cycle stages, whether it's new or code that's going into production, refactoring. Is this a one-off use of this code and then you don't have to go into production? Those would make very different needs. And then you have to look at all the different complexity if you're using different interactions from different code systems and your own, what the interactions are between your modules. So here are some good testing practices. We'll talk about code coverage, and then I'll get into that in a little bit more detail, but you need to verify that you have the code coverage you want. You need to have policies for dealing with both failed tests and issues that users come up with. Make sure you implement some type of issue tracking and come up with who's responsible, a priority scheme of what should be fixed and what time frame, and you can attach responsibility for each of those issues. Also, if you have a test suite, you should have someone that's watching the results from the test suite. Maybe you're running nightly and there's some results that need to be looked at. Assign somebody for that. Sorry, that went a little bit faster than I expected. And then when you're refactoring or you're adding new features to a code, then you need to make sure these regression tests are also run. And also, if you need to, you'll have to might need to make new regression features in your test suite. Another thing that sometimes is overlooked is test our code also, and you might want to make sure you do code review before you release test suites. Always having another pair of eyes on any kind of code change in your test suite is really cost effective. And then there are other test ideas. We talked about code coverage. One of the examples is using Github, which is comes along with your GNU compilers. It also has a graphical front end. It's pretty easy to use. You just compile with the coverage option and turn off optimization, and it actually counts the number of times each statement is executed. It works for C and Fortran, and there are other tools for other languages. We have them here, and you can look at that. Sometimes you can have the results pushed to a continuous integration server. Here's an example with a quick code, the heat equation example that we have. And you can see that it's run with this coverage. So this is a make file. So we add the coverage here and run the heat example, and then or the code, and then run Github. And you can look at the results. Here's just a quick example. It shows that some of these lines were run 500 times, some were non-executable, and these hash marks show that these are not being covered in this example, these lines. And here's an example of a graphical view. I'm not going to go into the details on it. It can actually get you down into the detailed analysis. But there are online tutorials for it, and you can look through those and figure out how to use it. So how do you build your test suite? There are two main purposes for your test suite. Regression testing, those can be very comprehensive and might be long running. And then there are continuous integration, which we'll have more detail about, gives you quick sanity check or diagnosis of any errors that you might be injecting as you check code in. So you want to make sure that you don't do that, and that helps with that. Also, we have a mix of different granularities. You might have unit tests for each component or even at the sub-component level, but you need to integrate them together. So you might have some simple configuration for doing some integration tests to make sure they play well together, and then system level tests. One thing I haven't mentioned till this point is restart tests. So many of the scientific codes are long running and we need more than one allocation. They may be run over several allocations or many allocations. And so they do checkpointing and restarting. So it's important in those types of applications that you test the restart, that make sure that they will work. And the rules of thumb, of course, are to try to keep it as simple as you can and enable quick pinpointing. We have useful resources on our Ideas Productivity site, and so we have a site to the how-to, a citation to the how-to site here. So there are two different, I'm going to go through a little bit of test development for two different types. It's different for new code compared to existing code or legacy code. And so your team is working on developing the code and is checking the code as they're going. So you can develop these tests at the same time and diagnostics at the same time that you're developing the code. And that's where test-driven development becomes a good practice. It's not trivial to devise good tests, but it is important, and you can try to do that hand in hand with your development. Sometimes you can devise tests that use a simpler analytic solution to test your components, and then build granularity into the testing. We'll have more examples of using scaffolding ideas to help build confidence in the components and the interface between them. And last of all, think about any test that you do that you might want to inject errors to make sure the test is working, that it shows when faults actually occur, it will catch them. And last, I want to talk about test development for legacy code. In the legacy code, many times tests don't exist or they don't cover enough, and we don't have the prior key developers available to understand the code. So what you can do is maybe isolate a small area of code that you'd like to start covering and dump a useful state snapshot for that code. Build a test driver. Start with just the files in that area and link in dependencies. Copy in any kind of optimizations. You might have to copy some of the dependencies and then customize them. And then you can read the state that you took a snapshot of, and now you have a new driver, and you can restart from that saved state. Then you can verify correctness, you can inject your own errors, but now you have a test that covers that part of this legacy code, and in incremental steps you can develop more and more coverage for the code and understanding. And so in summary, I'd like to say that you have a productive software team. They should be checking their work. They can take time to recognize the checks and make them into repeatable tests. Your test layout should mirror the logical structure of your code. Test each module and think about the dependencies between them. Use the idea of scaffolding if you need to test the different features on those modules with the dependencies of others. Different challenges are associated with the different types of codes, whether they're in production or they're just exploratory, or if you're dealing with legacy codes. Don't be distracted by all the technologies out there. Focus on exercising your code. Like I said before, David will go into a scaffolding idea that can help you, an example, and that gives you the idea what scaffolding is. And so I will see if there's any questions and turn it over to David. And I believe I'm still sharing, but you can take the controls.
All right, any questions for Pat? You can put them in the chat. You can raise your hand and unmute.
I'm trying to get where I can see the chat.
Yeah,
Oh,
I'll let you know. Unlike many of our tutorial presentations, we actually have enough time to really have some discussion here, so don't let us down.
Well, if there aren't any questions, we can save them for after we've done all of software testing.
Yep, Sure, we can. Please go ahead and continue. If you have a question as we go along, put it into chat and we will get to it as quickly as we can.
David, this is Phil Roth at Oak Ridge. I
Hey,
guess
Phil.
I'll ask one.
Sure.
So I definitely resonate with your statement that you said that each project has to kind of do their evaluation on their own about what they can afford with respect to this testing tax. Okay. But I'm wondering whether this is something where it's very empirical and people just over a period of maybe even years have to figure out what works for their project, or whether there are simple guidelines that people can start with that you would recommend.
Pat, did you want to address that, or do you want me to take it?
Go ahead, David.
So, you know, I don't think there are any detailed guidelines that would be useful. What I would say is get started with something to get over the barrier to entry. And then what you need to find, and Pat actually presented kind of a rubric for thinking about how exposed you are. What is the risk of bugs creeping into your code, right? And it depends in part on who's using the code and how it's being used, right? And you know, so how many people, is it used in production settings? How much, you know, is it used by other people as opposed to you or the, you know, just the core developers? And some things like that will help you think about how, you know, how exposed you are really, what your risk levels are. And that can really, I think, be a useful way to help guide the testing strategy. There's an organization in Germany, German Aerospace, DLR, that has a basically a guide they use within their organization that develops several tiers, and depending on these risk factors, essentially, you know, they advise sort of, it's not just testing, but software engineering in general. They kind of advise some software engineering practices that you should have in place, and things like that. So I don't have, you know, concrete examples, but a lot of it should be determined by the amount of exposure. And yeah, just, and also remember that the testing is something that you can build up over time, right? So you can, you know, you're obviously expanding the functionality of the code, and you should introduce tests as you're going along at some level. But then, you know, between production runs or development spurts or things like that, you might have some time to go back and add some additional tests in various places where you might be finding more bugs or things like that. Does that make sense?
Sure. The only unfortunate aspect of it that I would say is it feels like people are much more likely to be burned, you know, have something bad happen that makes them adjust, right? So it's either going to be they've committed too many resources to writing tests, or they haven't committed enough. But either way, it's going to be painful, right? And so that's part of the reason why, you know, it would be nice to have a little more of maybe a starting point where people hopefully wouldn't have such a big pendulum swing until they, you know, self-anneal to the place where testing really is the right place for their project.
Yeah.
So,
go ahead, Jim.
I was just going to say also that the PSIP process can help you with planning for that, possibly. That might be something you look into that will help you in that process of deciding where you should actually spend your time.
I was just going to say, so it's interesting you brought up getting burned on something, because one of the things that I was going to advise is to follow on to what David said about get started somewhere, get an infrastructure in place, is that if you do get burned on something, work that into your test suite so that it doesn't happen again, because it's embarrassing to get burned on something, but it's really embarrassing to get burned on something multiple times. But I've seen that a number of times where, you know, the same critical functionality breaks, maybe in a little bit of a different way or something. And then just to kind of bring some of that back together, Pat talked about coverage testing. And there's lots of limitations to coverage. It's certainly not a perfect metric, but it is a way to try to measure where you're at a little bit. So if you get started with it, look at what your coverage is. You know that if your coverage is 18%, your test suite is not good. If your coverage is 99%, it doesn't mean that your test suite is necessarily good. But one thing I found useful in, you know, the coverage evaluation is to think about you know, looking at really critical files, really critical kernels, and seeing, are those at least covered? Are there important paths of execution that aren't covered at all in my test suite? And so maybe, you know, getting from 55% test coverage up to 80% test coverage is not a practical short-term goal, but maybe finding, you know, really important pieces of the code and making sure that you add some testing for those spots specifically. That might be an approach that is practical.
Thanks for all the comments, everybody.
Of course, it's really hard to give specific advice about any of this, so we're always going to hedge a bit, but I think hopefully you can make something out of that. All right, so let's move on to the second part of the testing discussion. And why does this never want to stay on top? Okay, so this will repeat some of the things that Pat talked about, and we're going to try to dive into a little bit deeper on a few points. So first of all, how to think about building your test suite. As Pat mentioned, we want to think about development testing and continuous integration testing. So development testing may be long running. You want to try to provide pretty comprehensive coverage, as Jim just suggested. You know, 99 or 100% coverage may be unreasonable, but try to make sure your key kernels are covered and where you're encountering the most errors and things like that are obvious places. Continuous integration, on the other hand, which Jim will go into a great deal of additional detail about, is really meant to be more of a sanity check. It's meant to help ensure that during the development process, you're not introducing simple bugs which can impact really everybody's development practices. So you want to try to catch things before they get into the shared code base. And so the way to do that, in most people's opinions, is to have a set of tests that are fairly cursory. They check some basic things, but they do it quickly so that you can basically run them anytime you're doing a commit to the repository or updating a pull request. And as Pat also mentioned, you want to have a mix of granularities. Of course, you hear a lot about unit testing, and these names for different types of tests are a little bit arbitrary. Unit tests are usually considered to be sort of the lowest level and oftentimes connected with a program unit of code, a procedure or a class or even, you know, a function. And these, you know, those are good, and they allow you, there's a lot of useful testing that you can do at the unit test level. But as Pat also mentioned, it's really important to make sure that things interact appropriately. And so you need to build up integration tests, which take multiple components and make sure that they function properly together. And in a big complex code, you're probably going to have multiple levels of integration tests, right? You may build up some more complex module and have integration tests that show that that module is working okay, and then you may have multiple modules that interact at even larger scales, and you may need to test those to make sure they're interacting. And then, of course, the restart tests. And one of the reasons that restart tests are key are because it's really common, among other things, that you expose numerical issues with the restart tests, right? Depending on how things get written out and read back or recomputed or things like that, it's quite possible that some of the values in your state will end up being slightly different than they were when you wrote them out. And you have to understand whether that's going to be a problem or not. So starting your test suite, first rule of thumb is to think about simple tests, and always to think about tests that will help you actually pinpoint the source of the error. So, just understand it, just constructing some tests that says this whole big chunk of code is wrong isn't really as helpful as if you can construct a test that will help you isolate to, this loop or that if test or whatever. Okay, and so we have some resources that might help with this that are linked there. These are some additional ideas. So again, repeating a lot, emphasizing a lot of what Pat has already mentioned. You want to make sure, I would especially like to highlight these two down at the bottom, right? When you're refactoring code or adding new features, you want to make sure that you're testing, right? You want to have, ideally, you want to have tests that help you understand that the functionality that exists works properly. And so when you modify the code, when you refactor the code, you can rerun those tests and make sure that all those features are still working as they should be. And then when you're adding new features, of course, you obviously want to be testing the new features, but you also, once again, want to make sure that you haven't done anything that adversely impacts the existing functionality. Right, so it's good to think about those things as you're developing your tests and as you're adding or refactoring code. And then code review. Code review is a very useful practice both for the original code and for the tweets. And a couple of reasons. It's like peer review for a publication or something like that. It's another set of eyes that usually comes in with a different perspective and may not understand, may not have the same mindset that you do, and can be very helpful in spotting issues that you may not see initially. So code reviews are really useful for both the original code and for the test suites. And for the test suites, people think about things in different ways, and it can be really useful to help brainstorm with others, have somebody review your tests and say, oh, here's this additional thing that you could do that would test, help test this other aspect of your code and things like that. So let's dive in to a little bit more detail on a few things. So everybody, of course, now knows that when they're developing new code, they should develop tests along with it, right? There's actually a methodology called test-driven development, TDD, where you actually write the tests for your code first before you actually write a line of the core code. And then you build up the implementation in order to satisfy the test. Now, that's a strategy that many people will consider a little bit extreme. You don't necessarily, a lot of people, especially in our space, don't necessarily approach it that way. But I would argue that when you're developing code, you want to develop the tests that go with it right away while the code and the possible problems are fresh in your mind. You can always go back and add more tests later. But the biggest challenge is the practical challenge. We get distracted. There are other shiny objects. We're making progress towards implementing this new feature, and we want to get that done. And we can, the sooner we get that done, the sooner we can get the next paper out or something like that. And if you don't have the testing to go with it, you're likely to run ahead with the implementation and not be able to give yourself proper confidence in the quality of that code. But it becomes harder and harder to devote the time to just developing the test to follow along. So doing it together is a really useful thing. And then there are a lot of different ways to test. As Pat mentioned, a lot of things can't, a priori be tested as you might want. So you have to think about strategies. For example, maybe there's an analytic case that you can test through the code. Or maybe there are, constructed, very artificial kinds of solutions, but they can test different aspects. You may not be able to test everything with a single test, right? As we've discussed, you want to build different granularities into the testing. So unit tests are good, but also higher level tests as you start hooking things together. We'll talk in the next few slides about some ideas of scaffolding to help build confidence. Always test your tests. So actually put bad code, put errors in your code, run the test to make sure that they actually evidence the errors when they're supposed to. And so these are all practices that you can really develop some facility at as you're going through, and it can become quite natural. Now, in terms of how to structure your tests, we talked about wanting to try to pinpoint bugs. So one of the most useful ways in code to think about this is start from the bottom up. So you can take a unit and get some confidence in it, and then you can start connecting those units together. And so sometimes you may not be able to fully exercise a dependency. You may not have that unit fully tested. You may not be able to have full confidence in it yet. So you might have, unit tests for one module, unit tests for another, and you might have some additional tests for the combination of those, where you're doing, you're mocking up functionality from one of the modules. Because it's too complex, or because you don't have that one fully tested yet. So you have to kind of start somewhere. And you want to build these things up in layers. And oftentimes you can kind of go back and forth to build up things. And we'll show that in the next couple of slides here. So one example that's fairly common is a Halo exchange type of thing. So you can devise a test for that makes sure, just by filling your grid with different functions in the core and in the ghost cells, and then doing the Halo exchange and checking to make sure the data has been properly moved around. So you can develop, with a test like this, you can develop confidence in your grid cell level unit, right? Another unit in your code, example is coming from the Flash astrophysics code, for example, is equation of state. So how do you build up testing for the equation of state? Well, there you're putting in, you're saying some things are known in the equation of state and you're computing others. And one common thing is to sort of rotate those around through all the different combinations so that you can check your synthetic inputs and against the synthetic outputs from testing the equation of state and making sure that it's all consistent. And then you can put these things together and say you want to test now the hydrodynamic solver. So there's a simple problem called the set-off blast wave with a known solution and known analytical solution, which makes it really useful for testing. And so we start out with the mesh, and we also need the equation of state, and we verify individually the mesh and the equation of state, and then we combine those, we integrate those with the Hydro module. And so now we can gain confidence in the Hydro module because we've already tested, we've built up this scaffolding of confidence because we've already tested individually the mesh and the equation of state. And because we're doing this in a stepwise or layered fashion, this kind of seems a little bit tedious sometimes, but in complex scientific codes, it's often the best way to gain confidence, and you should understand with a diagram like this that it's not impossible to test the Hydro code, but you have to develop the confidence in the things that it depends on first in order to understand that the Hydro code is actually what is being tested and focus down, be able to pinpoint the errors. So if we're going to do this with an adaptive mesh, as the diagram shows, instead of a simple regular mesh, then we have to get more complicated, right? And so now we want to introduce the AMR module. Okay, so AMR is a pretty complex operation all on its own. So let's start with the tests that we had before, and now let's, so we've gained some confidence in the Hydro module. So instead of the basic regular grid, let's swap in the AMR, but let's turn off all the fancy features of AMR. So it's really just, a basic grid. And if we can replicate the tests with the basic AMR module, then we have a good start. Okay, if the problem, if the basic AMR module can't just replace the mesh, then we have more fundamental problems that we have to investigate. Okay, but then we want to turn on the dynamic refinement capabilities in the AMR. And that gives us kind of an additional layer of testing in the AMR. And we've already gained some confidence in the Hydro and the equation of state, so we can build this up, right? And so if this test, if this test fails, then there's a problem with the flux correction algorithm. And if this test fails, then we would find the fault to be in the regridding capabilities. So you can, even within a complex module, you can layer these ideas up by incrementally enabling the more advanced functionality. And now, actually, I didn't realize that Pat was also going through this whole legacy code example. So this is, I'm going to have to unfortunately flip through all the animations here, but it is kind of a challenging case. So let's talk through it a little bit as we go along. So the idea here is that you want to isolate a piece of the legacy code in order to be able to test it, but you don't have, you may have some inputs and outputs for the whole code, but you don't have anything that applies to this particular piece of the code. You want to isolate it so that you can refactor it, for example. So what we do is we run the whole application and we write where that code comes off, that little module that we want to test. We capture the state as an input to that little module that we want to test. And we construct a driver that will call out from the legacy, or will replace the rest of the legacy code. And I don't want to actually talk about that piece right now. So this driver is going to actually read in the state and pass the state into this little module and invoke the little module that we want to test. And the other challenge you have in cases like this is that oftentimes there are complex dependencies in a large module like this. And if you want to just start pulling in satisfying all the dependencies, you're going to pull in a lot of code. So sometimes you have to do that, but sometimes you can isolate just small pieces of functionality rather than pulling in whole modules. And if that's possible, that's oftentimes valuable, because the less external code dependencies that you have, it simplifies things, gives you, makes it easier to focus down on where the problems might be. So you can take the little red dot, which represents one of these little dependencies, extract it out and associate it with the driver. And so now you have this new little application down in the bottom, which is capable of testing this little module that you've extracted from the legacy code. And this is the kind of thing that you can do pretty quickly, just a couple of days. This was done with the E3SM code to help isolate a portion that was really too hard to test. And what it did was take the testing process down from, running the whole E3SM model for days or weeks to get to the state where you needed, to having this little chunk of code that you wanted to test and being able to run it in a matter of a minute on a laptop instead of having to go out to some big cluster. And so this is a very useful strategy for legacy code. And remember, the definition of legacy code here is merely code that doesn't have adequate testing to give you confidence that when you work on it, you're going to get the same thing the same functionality out that you started with. So now we've got a bunch of tests, but it's a large, complex code. So we want to think about how to test efficiently. And so this is not just your team's effort to develop the test, but this is also the execution time for your tests and things like that. Because you can't just spend all of your allocation running test and test and test all the time. So a useful strategy for that is to map out your code in a matrix like this, where you're putting the modules across the rows, and across the top, you have the different kinds of physics, essentially, that you want to model. And you start thinking about all the tests that you have and what do they exercise, right? So you want to think about all of your unit tests, and what do they exercise. So here's the CL test exercises Hydro and EOS with the AMR module, right? So here's your infrastructure, and here's your physics modules. You want to look for tests that are going to be the most sensitive to perturbation. So if there's any variation in the data, you want to find the things that are going to raise that up most quickly and most easily. And for example, maybe the set of tests that we mentioned before is a good test with a uniform grid. And that works also if you have particles in the mix. And then maybe you have, you need to, of course, test your solvers. So you want to look for the most stringent test for the solver. You can construct lots of different tests for the solvers. But you want to start with the most stringent ones that you can manage to gain the most confidence quickly. And so you develop this matrix, and then if not everything needs to be filled in, some things just don't make sense physically, but you need to make sure that all the areas that are worth covering get covered, and you want to fill in those additional areas with the least complex test that can cover the remaining spots. And this process can also help you identify where some of the gaps are in your testing that you might need to spend time filling in. So why not always use the most stringent testing? As we've discussed, there can be a lot of work here, and it can take a long time to run the tests. So it's really useful to think about these things as a team and to evaluate what the project really needs. We'll go back to what we discussed before. What are the expected uses of the code? Where are you in the life cycle of the code? what's the composition of your team and heterogeneity? How much effort can people afford to put into it? And do you have the expertise that you need for all the different areas? Where are you in the production cycle, or is this a one-off code? And then how complex, analyze how complex this code really is to help guide some of your thinking about these things. So the takeaways, you want to understand the context to help understand the testing needs and the costs that are associated with it. You want to try to devise tests to enable quick pinpointing of errors, and you can build up a lot of complex tests through reasoning incrementally, or layering different capabilities and understanding how they interact. You want to ensure that you have testing at various granularities, as much at the bottom as you can, but don't forget the integration testing and the higher level validation testing. That's also very important. Think about tests that you can run very quickly in a CI context, which Jim will talk about, and things that you might want to run periodically as longer running tests. And you really want to think, you don't want to drill down and focus strictly on CI or strictly on anything else. You want to have a holistic strategy that ensures that you have confidence in the whole code and that the science that's coming out of your code is correct. And how do you gain that confidence? And with that, we can take a quick break and answer more questions while Jim prepares his slides. Any questions?
I guess I'd have one question, is how you would approach this if the team was a little bit less, how should I put it? If it was a little bit more delocalized, certain people were working on one piece of code, another, so it wasn't sort of a team in the sense that, say, there were 4 or 5 members, all of whom were concentrating on the same piece of code, but more of a loose collaboration.
Yeah, so that's often the case, especially in my experience, at least, of a lot of DOE projects. Of course, the testing occurs at multiple granularities. So there will be some kinds of tests that the team, a localized piece of the team, can think about, work on, and reason about. But there's going to be some kinds of testing that's going to need cooperation and interaction, just like the code cooperates and interacts with other parts of the code. And at that point, you need to be getting the team together and talking through things and trying to make sure all the bases are covered. Now, one thing that is very useful from a sort of software engineering standpoint, and also oftentimes happens fairly naturally, is you get strong interfaces between different components that are being developed by different groups. If different groups are not sort of in each other's code, then you probably hopefully have good, strong, solid APIs between the two that are pretty well defined. And that kind of experience can help a lot with testing strategies, because you really need to focus on the APIs doing, you have kind of a contract between the caller and the callee, and you can focus on what's in that contract, and you don't have to worry about the implementation that's underneath, as long as you're testing the API and it's doing what it says it's going to do. But there is no avoiding some level of discussion and engagement around some of these larger scale integration tests and things like that. And certainly for the overall verification and validation of your code, you need to have a team level strategy that everybody buys into.
Thank you.
All right, Jim.
All right. Can you see my screen?
You're good.
Yes.
Excellent. All right. So we've talked about CI quite a bit already, both David and Pat, but we haven't really talked about what CI is yet. And so I want to start there. The tests run for CI testing tend to be a curated, sometimes even a different set of tests than what you use, for example, for nightly testing. CI tests exercise critical functionality and run relatively quickly in most cases. For a smaller project whose test suite runs in just a few minutes, the running quickly part may not be so consequential, but for projects that take hours to compile and test, this notion of speed becomes a lot more important. The integration piece of CI speaks to testing to ensure that things will continue to work. David talked about that some. There are tests run with every change to the code base. The test might be run just before a merge, preventing the faults from ever getting onto important branches, or they might be run just after a merge in a way that allows developers to very quickly identify which specific changes led to the fault and to fix or revert those commits as necessary. In most cases, it's better to never let the fault be committed to the important branch. This isn't always practical. One example is that integration testing can take place at multiple levels. You have your individual project, but there's also CI testing for SPAC and for E4S, the Extreme Scale Scientific Software stack. So when you have a change to one of the individual projects, it's relatively simple to say, well, unless we pass our own test suite, we're not going to allow this into the branch. But to force an individual project or even promote that an individual project require that a much larger suite of tests across many different projects pass before they can get changes into their branches, that can be prohibitively complicated, and it can lead to not making changes for reasons that have nothing to do with your code. So that's just a long-winded way of saying sometimes this testing happens just before a change, sometimes just after, sometimes a little bit beyond just after if you're testing many projects together. But the idea is that it's not testing huge chunks of development, develop, and then merge and test. It's doing this in relatively small bite-sized pieces. Why isn't this advancing? Here we go. All right, the next distinction I want to make is just between automated testing and continuous integrated testing. The term CI is really popular right now, and it's used in contexts that go beyond what would be categorized as CI by strict definition. Within ECP, there's a CI effort, for example, and this is a very important effort. But I just wanted to say that all of the ECP CI effort is not focused around what would traditionally be called continuous integration. So some of the ECP CI effort really focuses on providing access to different platforms where CI style testing, where you're testing things very frequently and at very fine granularity, that may not be practical on some of these bigger machines. You may need to bundle up lots of commits, maybe from across multiple projects in order to get the cycles there. So again, not to take anything away from that effort. It's a hugely important effort, but it's just a little bit different. I think it's called CI for simplicity, but in the strict definition, it may not be CI. Automated testing in general reliably detects and reports failures and is in some way automated. So you might consider executing C-test or just your nightly testing in a generic sense, or make check to be automated testing. It might be useful to think of this as often living next to your development workflow. The nightly tests just happen overnight, for example. It's not tied into direct development of the code. If it was a holiday and the tests were scheduled to run and there were no changes to the code, it's going to run just like the previous day. So there's some potential problems with automated testing in a general sense. For example, the nightly testing, maybe due to resource limitations or whatever, the timeliness of how long it takes for the results to run, it doesn't run with the same level of frequency and granularity. So it may be difficult to figure out which of the changes that were tested for the first time in this run of the automated testing, which of them led to the failure. You might need to do some bisecting to figure that out. So that's just a little bit of the distinction between automated and nightly testing. So examples, on the left here, we have automated testing that reports nightly to a dashboard. You might also hear often you might think of CDash. A lot of projects use CDash. Here is an example of a homegrown testing dashboard. Whereas the CI testing, more on the right side here, this testing lives literally embedded in your development work in a lot of cases. Here you see within a GitHub pull request that the green merge button, this can be configured in such a way that that button is not clickable. You cannot merge it until the Lighthouse set of tests has passed, and the Travis here in this example set of tests has passed. So it's literally part of the development workflow. It has to be completed before you're even allowed to merge. Next, I wanted to focus on some of the challenges in CI testing. One of the biggest overall hurdles is often just getting started, getting that very, very first test set up so that when you want to set up the next test, all of the infrastructure is in place. All of the processes for setting up a new test is in place. That is often maybe the biggest hurdle for projects getting started. So we'll talk about that just a little bit. Our suggestion there is to just start really, really small. In the most basic case, maybe just start with a very simple out-of-the-box CI solution and just compile your code even. You want to have a set of CI tests that you run and such, but maybe at the very beginning, you just compile your code and make sure that when things get committed, it compiles and then you add testing later. Another common challenge is developing suitable tests. Existing test suites aren't suitable for CI in many cases. How long does it take to run? Does it take too long that developers get antsy getting results? Are there tests in your test suite that have really tight tolerances and maybe occasionally fail? Are there unreliable platforms that you're looking at testing on and sometimes tests there fail? There's many challenges to developing a suitable test suite, but development teams understandably can get very frustrated if they are seeing feedback in the testing infrastructure that is not due to changes that they made, errors that were for other reasons. And then certainly ensuring sufficient coverage. I'll talk about this, maybe in a different angle in the summary piece, but you're really only as safe as what your tests are testing. I've seen people say, well, I ran the test suite. Well, going back to some of the discussion between Pat and David's talks, I think that was the part where we talked about it. What is enough coverage and how do you add that coverage? And does running your suite of tests provide the assurance that the critical functionality is tested and tested properly? and test it in the right ways. So some more advanced situations, I already talked a little bit about inconsistent failures, but sometimes just moving a test from one platform to another, I'm sure many of us have experienced that. The tolerance needs to change a little bit. There's many challenges there, but that's another reason why CI can be difficult. Dealing with lots of third-party software across many different platforms. And here I would even add, giving your developers access to all of this third-party software in some cases can be challenging. And so if a developer gets feedback that says this test has failed and it needs to be dealt with, do they have the ability to reproduce that? Is the infrastructure in place to allow them to have access to that third-party software, to the right platforms? That can be certainly a challenge in CI, enabling your developers to deal with the issues that they're seeing reported. And one final advanced situation is performance testing. And I'll move on. I don't want to spend a lot of time there. So where do you run jobs? There's kind of two broad categories of where CI resources can be run. One is out on the cloud. There's many free or relatively low cost options here, many of which have a higher level of paid access. And then the other general category is site local. So maybe you're using Jenkins or GitLab CI. And so these are resources that you provide to yourself in essence. A lot of these other ones can be built into GitHub. We saw the Travis example where it was literally reporting back into a GitHub pull request, for example. And I wanted to say here that I think David touched on this very briefly, but the cost model for Travis CI has evolved. And so this tutorial used to go into a fairly in-depth Travis example. We haven't really had a chance to fully digest that change to Travis, so it certainly remains an option, but we're going to be looking at other options into the future, which is fine. Travis CI was a very early player in this space, but there's lots of other ones, including Circle CI and GitHub Actions that are just freely available, and a person can get started there. So we're not endorsing right now a specific service. They're all a little bit different. They all have a lot of similarities. So I talked through some of the examples already. I did want to point out ECP has some CI resources, and there is still an effort towards a complex-wide CI experience where you can have your jobs run across a broad set of machines at different sites. This complex-wide federation is still very much in development, but there are site-specific CI solutions for every site now. And so there's a lot that people can do right now, even without this federated runner model. And so I really wanted to pitch a couple of things that are coming up. On Wednesday, there's kind of an overview of ECP CI. And on Friday, there's an afternoon tutorial that focuses on how to get started with ECP CI. I would encourage a lot of you to attend that and just kind of dip your toe in. There's some people who can help you with this. There's documentation at this ecpci.gitlab.io. And getting started with ECP CI can be a little bit more complicated, perhaps, than some of the freely available lower power, if you will, solutions, and you may want to start there. But I would also encourage anyone who's on the ECP project to try to get plugged in there. Many different groups have already been plugged into it, and there are some people who can help you out with getting started with that. You know, better hand-holding than some of the simpler online solutions. So putting aside for a moment where all of this stuff is supposed to be run, there's the issue that was mentioned early on of what tests are, you know, right, and where is a small place to start. How do you get started with CI? How do you overcome that first hurdle? And I would encourage you to start with just one configuration, even just one single configuration that you think is the most important. Protect that single configuration with every single commit and build from there. I've experienced that exact approach. You get a disproportionate amount of the overall value from the first configuration as compared to adding another and another and another and another and another. It's great if you have 60 different CI configurations, but getting that first one is a really big deal, and it also sets a template for setting up the other ones. And then, you know, what functionality is the most important? What are you trying to protect here? Maybe you start with a very basic configuration and then move to others. So again, there is no starting too small. You know, the very first thing you get from CI is just making sure that things don't get generally broken after a commit. You can still configure your code. You can still, you know, build and execute it, you know, generally speaking. So I would encourage you to just start small. So just a little bit of example here as to how you might set this up. I told you all of the services are a little bit different in how they handle things, but we will look a little bit specifically at a couple of them. With Travis CI, this can be very, very simple. Just specifying what language and compiler you want to use, a scripted configuration of, you know, you just pass a make command with some CXX flags values. Here, we're also passing an LD flags value to turn on the coverage testing, and then the make target check all. And it's just what you type at the, you know, command line to execute this yourself. And then after this after success is a keyword that says after a pass, I want to essentially pass this to the code coverage tool so that I get some results there. And so it really can be that simple. And the after success, you don't even have to start with that. Starting with the coverage, you don't even have to start with that. So just to give you an idea what this looks like then, like I said, we're not going to run through this example today, but in Travis, you see here some different runs of the CI testing. And then here is one example output from the code coverage command that I showed on the previous slide that just gives you a breakdown by file of the code coverage that was achieved during that CI run. I wanted to show you just really briefly an example from GitHub Actions as well, and some of the things that you can do here just to motivate the use of this. Here is a listing of the recent tests for a project. I want to thank Miranda Munt for providing me with some of this content for the GitHub Actions infrastructure for the project called Pyomo. And this shows for every pull request, whether it passed or failed. It's pretty obvious. Green is pass, red is fail. Here it is at a pull request level, just kind of a different view of similar results. The green check mark again showing that it passed all of the tests. The red X meaning that it failed some. This, I don't want to go through this in detail, but GitHub Actions has a somewhat similar approach for defining what its tests are. Namely, there's a name on the top, and then how is this triggered? For example, here it shows that it's triggered by every push to the repository, and then the branches. And so it's a little bit more involved than the Travis example, but still not overly complicated. There's a definition of all of the different jobs. You can do a wide variety of things here. This does not have to be overly complicated. This example has a bit of complexity, testing with different versions of Python, testing with different OSs, and it specifies timeouts, things of that nature. So there's a lot of things that a person can do with GitHub Actions. And then steps, this one checks out the Pyomo source code and then configures different jobs. Again, these are a little bit more advanced just to motivate where you can go after the more basic start. But Pyomo here, for example, has managed to automate their entire release process and the creation of all of their release tarballs on several different platforms, OS X, Windows, Linux, and a generic release as well. And so once you get by those initial steps, and that's exactly how Pyomo did this too. They started very, very simple, and then they just built bit by bit over a period of, I would say over a year now. They've just been kind of adding to this. And so now they have a pretty advanced infrastructure, but they started pretty simple. So just to very briefly summarize, CI testing, the purpose is to identify problems early. We don't want to wait. The sooner that you can identify them, the quicker you can pinpoint them and get them fixed. CI testing should complement, but not replace the more extensive nightly testing, but there may not be time at each commit of the code to run an entire nightly test suite. There's many options for getting started, and start simple. With that, we're down to the last couple of minutes. I'd like to move to the summary presentation. Okay, so I just wanted to point out in summary that your test suite really, really matters. What Pat was talking about and what David was talking about with regards to setting up the right thing, building up scaffolding, that really matters because there's lots of other efforts going on in ECP related to testing. I mentioned the SPAC CI testing. There's E4S CI testing. There's release testing. There's testing that facilities people do when they install your software. If you don't have a good test suite to begin with, and one that is targeted, is reliably passing, not giving a lot of false failures, that whole pyramid, it just doesn't work. It really is important to have a really solid base of testing so that that entire pyramid can be built up to the very top, and so that you don't get this false sense of confidence that, oh, I ran the tests and they passed, that there really is some meat. So in this brief tutorial, we covered just a couple of topics today. We looked at testing, we looked at continuous integration. There's a lot of other topics that the IDEAS BSSW team looks at. We didn't have time for these topics today. Now, you might look at that list of topics and roll your eyes and say that you can't spend all of your time on software engineering issues. We completely agree with you. As was mentioned earlier, I really would encourage you to look at this PSIP process, the Productivity and Sustainability Improvement Planning. It allows you to look at these things and bite off just tiny pieces at a time. And start from there, build just a little bit, very much in the same vein of thinking as getting started with CI. You can do that with any of these processes, with any software engineering issue. And so with that, here's some ways that you can keep in touch with us. We have a mail list and we have different websites. Please feel free to follow up with us in the chat quickly now or here. And again, quick pitch for these things coming up. There's a couple of CI things on Wednesday and Friday and some other very relevant presentations throughout the week. David, did you want to give any last words?
Yeah, I just also wanted to point out that we've got a room in the GatherTown side meetings area, room 125, that will have some ideas people populating for about an hour and a half each day this week. So please feel free to drop in and chat with us there if you want. And it's not only about testing. We can talk about all kinds of other things there. And I want to thank everybody for their participation. We're at the top of the hour, but I at least can stick around for a few minutes. We can deal with some additional questions. And
Yep,
we'd also love
too.
to have feedback. Thank you. If there are no questions, then thank you very much again for attending.
Actually, this is Elena Purmli. I have a question. I was
Sure.
typing too slowly. Do you have experience with setting up performance regression testing? For example, for HDF5, we discovered that all our work in some cases end up in regression in performance. And I think it's very important, first of all, to be aware of this thing and then emphasize and have some kind of best practices how you set up performance regression testing.
Yeah, that's a very important point, especially in our universe. And performance testing can be a challenge because many of the cases you might want to use for performance testing would be larger scale and things like that. And it's hard to afford to run them too often. So yes, performance testing is very valuable. You need to make sure you have a way of capturing your metrics and being able to go back and look at them over time and see how they change. That may or may not be something that you need to automate, especially in part depending on how frequently your tests are being run. You might want to think about running at least some of your larger scale performance tests on a less frequent interval, just to be able to sort of verify things. Maybe some simple performance tests can be built into your more routine testing. There are some tools, I think, in the performance world that can help with some of these things, like performance databases and things like that can help collect performance information as you're going along. So those are just a few ideas. Others may have thoughts on those, including folks in the audience.
Yeah, thank you. And I believe having something for software stack will be very useful.
What can you expand on that?
For example, and once again, I'm talking from HDF5 point of view, there are several packages and applications that build on top of HDF5. And if there was some regression testing for the whole stack that uses HDF5, MPI underneath, and different file systems underneath, things can be caught earlier than later between releases, etc. So, for example, we see in some regression for some specific use cases that we didn't have chance to test. So having that information would definitely help middleware software to be better, right?
Yeah, that's definitely true. That's kind of, I think of that as an example of integration at even a larger scale.
Right.
Right. Testing even outside your package.
Right.
And things like that. And yes, that can be very valuable. So I would say, things like E4S provide, I think, some potential to help with that situation. Of course, I think most of the focus right now is on smoke testing the individual packages, but you can imagine that being a useful environment to enable more extensive testing where you have a pretty well-defined set of all the modules that are interacting. One of the challenges in just some random environment, in my experience, is being able to clearly identify and probably control all the modules that are involved, so you know what the what's really being tested and what isn't. in terms of versions and such. And if you can do that, if you can say, hey, this has been tested this way with E4S, this release or whatever, then you can define that for people a little bit better and for your own thinking about where your tests stand.
So this is Chuck Atkins. Hi, Elena. I'm with Kitware, and I mean, obviously, I know Elena, but you know, I have not met you personally. But so we've been actually, and this may be interesting for the rest of the audience as well. But so this is something we've been actually working on, this very problem with Audios, with the Audios project, and because we were running into the same kind of thing of wanting to actually track kind of performance benchmarks over time, and we've been working on actually integrating that with CDash, and because it's already using CTest and CDash for the regular testing, and you've got this dashboard platform, and so we're working on essentially having benchmark tests that can output kind of arbitrary values for like megabytes per second when reading, and runtime to do these particular tasks, and kind of output individual metrics with a given benchmark test, and then kind of enabling CDash to kind of view and plot those over time alongside where you would normally have your other testing results. And so far we're kind of showing some good promise with that, and the kind of capability is kind of there, and I think we need to try and come up with a maybe a more intuitive kind of user-facing front end on how to view that. But as far as being able to kind of track the results and submit them into a singular place and that sort of thing in a way that already integrates with your existing testing platform, that's something we've been working with on CDash.
Yeah, CDash is great, and we use Grafana also because we have our regression, performance regression testing results, and plus we integrated CMX.io and some other known benchmarks in HPC. But the point is that, parameter space on which you test is so big that you cannot test everything, right, and create. So having this, some kind of focusing on applications and their access patterns will help for software in the software stack to catch the issues. And it will be good if ECP kind of first raises awareness of performance and then works toward unified performance testing framework where really those packages are tested more rigorously. I just wish we have it where HDF folks will be poked earlier than later. That's when regression is seen.
Yeah, performance testing is an incredibly rich topic. So I have a colleague at Sandia who wrote a tool, he and a couple of other people, that does a pretty good job of allowing people to designate tests and then dig down into performance changes and graph performance changes across time. But I think this is an example of one type of testing that hasn't been done really well in the general universal case. There's a couple of dashboards like CDash out there that people look to for that kind of general capability, but there isn't really a de facto standard yet. And then the other thing that's really challenging, I think, about performance testing is how many different angles there are about it that can go wrong. If a machine is overloaded too much,
right?
What change in performance do you flag as a failure that you want to be notified of, or do people have to proactively be monitoring this all the time, or how often can you actually run? How big of problems can you scale up to? What is representative enough? If you're testing the performance of an application, there's several layered software layers there, and a change to any of them, as David kind of said before about tracking versions of this and that and that and this, and it becomes a pretty complex space to be in.
Yeah, but it will be good to start working in that direction.
Yeah.
Thank you.
As with most things, start simple. Do something.
I have a question for you guys.
Sure.
How strictly do you adhere to the Scrum style? I guess no development can proceed until you kind of have a failing test and go from there. How do you balance that with actually getting work done?
So I would consider that to be a characteristic of test-driven development as opposed to Scrum per se. I would, in my experience, I think few people really follow TDD, but it's useful to keep in mind, but it's maybe, I don't know, I think a little bit too strict, at least from my perspective. Others may well have different experiences, though. That's really a personal observation.
So I think personally trying to balance it with getting work done, I get that. I think one of the risk, of course, is that when you permit kind of failing tests to go unchecked, then it kind of becomes a broken window syndrome, in the sense of like, well, then eventually like nobody really pays attention because the dashboard's always red, and but that kind of goes back to the type of tests that you have, and if you have tests that are flaky and maybe pass sometimes, not others, then maybe that's not a good test to have as a like this has to pass. And so a lot of times it ends up being just kind of putting the work in up front to like have a green test suite that's always passing, and then from that point on it's easier to maintain. But if you kind of start off where a bunch of stuff is broken, then it's hard to kind of keep it that way.
Yeah, and the other thing that I would add to what Chuck said is, if you can move something to pre-push, where you are forcing things to pass before you can hit the merge button, you find those tests that are reliable, reliably passing across platforms, establish some kind of solid base. That can help the stability of your code tremendously. Maybe that doesn't touch certain platforms that are a little bit more finicky or more developmental. Maybe it doesn't touch certain tests in your code, but identify some solid subset that are, and start very, very small if you have to. But I think, I know of projects that have been around for 20 years that have never had a day in the life of the project where the entire dashboard is clean, and across all platforms. And I've also seen one, that was around for more than 10 years before that was achieved, but now in a certain subset of platforms, in a certain subset of configurations, that is now enforced, and it's not even an option. And when developers have to deal with that at the time that they're pushing, I think it's actually a lot more simple for them overall. It's not a fire drill. They can take their time, they can get it fixed, they can do it right. If they deem that test failure isn't important, they can disable that test for a while if they want to, depending on policy. But I would just really strongly encourage what Chuck said of working hard to getting something that's green.
Any other questions or comments? Thanks for some great discussion, folks.
Thank you.
Thanks, David.
All right, I think it's time to declare victory.
Bye.
Thanks all, bye.
Thanks everyone for attending, bye.
Thanks for
Thank you.
coming.